Introduction: a universe alive with possibility. Look up at the night sky, and what do you see? A scattering of stars, a canvas of darkness pierced by distant suns, a quiet and ancient light. But behind those faint glimmers lies a question that has echoed through centuries. Are we alone? For physicist and storyteller Brian Cox, this is not merely a scientific question. It is a deeply human one. It is a thread that runs through our myths, our philosophies, our mathematics, and now through our telescopes. To wonder about life beyond Earth is to wonder about ourselves, our origins, our uniqueness, our future. In the last few decades, our ability to peer into the cosmos has evolved dramatically. Where once we knew only the planets of our solar system, today we know of thousands of worlds orbiting distant stars, many of them potentially hospitable to life. But the leap from habitability to actual life remains vast. Brian Cox approaches this gap not with certainty, but with wonder. He invites us to consider a universe not as a barren void, but as a place where life might be common, or at least beautifully possible. This audiobook is not about proving life exists elsewhere. It is about exploring the conditions that make life possible, about following the clues carved into light, chemistry, and gravity. It is about moons with oceans beneath ice, atmospheres laced with strange chemicals, and stars older than time itself. But it is also about something more intimate. It is about what it means to be alive in a universe this vast, about how the search for life out there changes the way we see life here. It is about hope, loneliness, imagination, and the breathtaking realization that life anywhere is extraordinary. Brian Cox reminds us that science is not just a tool for discovery, it is a window into awe. And in this search for a cosmic company, we find not only the distant possibility of alien life, but a mirror reflecting the fragile miracle of our own. So let us begin this journey not with answers, but with eyes wide open, because somewhere, orbiting a quiet star beneath a sky alien and beautiful, something might be watching the stars too. Chapter 1: Origins. How life begins. Life, as we know it, is a phenomenon so intricate, so delicate, and yet so persistent that it seems almost inevitable in hindsight. But how does it truly begin? What invisible spark transforms lifeless atoms into a living cell, to something that moves, consumes, replicates, evolves? Brian Cox often frames this question not merely as a biochemical problem, but as a deep mystery that touches the essence of what the universe can become. In his view, the emergence of life is not just a stroke of chance, but a testament to the laws of nature, laws that under the right conditions, may lead to life as naturally as gravity shapes the stars on Earth. Life began more than 3.5 billion years ago, perhaps earlier. The earliest forms were simple microscopic, single-celled organisms that left behind faint traces in ancient rock. But even these basic life forms required a complex interplay of chemistry. Organic molecules, such as amino acids and nucleotides, must have assembled, concentrated, and linked together in just the right way to form the building blocks of biology. Where did this happen? Some theories suggest life began in deep-sea hydrothermal vents, where mineral-rich waters provided both energy and structure. Others point to shallow pools, where evaporation and sunlight could drive chemical reactions. Some even propose that the basic ingredients of life arrived from space delivered by comets or meteorites, carrying organic compounds formed in distant clouds of gas and dust. Brian Cox doesn't claim to have all the answers, but he emphasizes the importance of context. Life didn't appear in defiance of the universe, it emerged from it. The same physical laws that govern the stars also guide the formation of molecules. In fact, laboratory experiments have shown that under conditions similar to early Earth, simple organic molecules can form spontaneously. The raw ingredients, it seems, are not rare, and that leads to a thrilling possibility. If life on Earth arose from natural processes acting on common elements carbon, hydrogen, nitrogen, then perhaps those same processes are playing out elsewhere right now under alien skies. Across the galaxy, countless planets orbit their stars. Some are rocky, some icy, some cloaked in clouds. But on a few, the temperature may be just right. There may be water, energy, and time. And where those ingredients come together, perhaps, nature does what it did here. It builds complexity, one molecule at a time, until something stirs. But life, even in its simplest form, is not merely chemistry. It is chemistry with memory. It evolves, it learns, it adapts, and perhaps most mysteriously, it becomes aware. This is where Brian Cox's perspective deepens. He often reminds us that the universe is not simply a place in which life happens, may in some way be a universe that makes life possible. The laws of physics, the constants of nature, the stability of atoms all seem finely tuned for complexity to arise. Is this design coincidence or something deeper? Science doesn't yet know. But in the absence of certainty, there is wonder. There is curiosity, and there is an open sky filled with unanswered questions. The origins of life may still be shrouded in mystery, but the search for understanding is part of the very process life itself enables. We look outward because we were born to ask. We explore because somewhere in the folds of molecules and the silence of stars, we sense that we are not alone. The beginning of life, then, is not just a scientific puzzle, it is a story still unfolding. And in every question we ask, we take one more step toward discovering whether this story is ours alone or one chapter in a greater cosmic narrative. Chapter 2: The Goldilocks Principle. Not too hot, not too cold, but just right. This simple phrase, borrowed from a fairy tale, now echoes across astrophysics as a guiding principle in the search for life beyond Earth. The Goldilocks Principle, so named because it seeks that delicate balance between extremes, describes the fragile conditions that might allow life to arise and endure on other worlds. For Brian Cox, this idea is far more than a checklist of temperatures and chemical conditions. It is a profound reflection of the precision of nature. That life exists at all suggests that somewhere in the infinite spread of space and probability, a balance has been struck, and perhaps it is not unique at its most basic. The Goldilocks zone refers to the range of distances from a star where a planet could sustain liquid water on its surface. Too close, and the water boils away. Too far, and it freezes solid. But within this narrow window, water, a universal solvent, a carrier of nutrients, a medium for chemical reactions, can flow, pool, and cycle. On Earth, water is not just essential to life, is inseparable from it. But the Goldilocks Principle is not merely about distance. A planet's ability to hold water depends on many other factors: its atmosphere, its mass, its magnetic field, its geology, and even the nature of the star it orbits. Consider Venus, Earth's sister in size and composition. It orbits just a bit closer to the Sun. Yet on its surface, temperatures soar above 460 degrees Celsius, and the atmosphere is thick with carbon dioxide, acidic clouds, and crushing pressure. Whatever chance Venus had to be just right was lost in a runaway greenhouse effect, now turned to Mars, colder, drier, and smaller than Earth. It lies just outside the traditional habitable zone. But in its ancient past, evidence suggests that rivers once ran across its surface, and lakes filled craters under a sky thick enough to keep water from vanishing into space. For a time, Mars may have been close to just right as well. These planetary comparisons highlight something essential. Habitability is not a static state. It is dynamic, evolving, and often fleeting. A world that is habitable today may not be tomorrow. And a seemingly hostile planet may once have been home to oceans, clouds, and perhaps life. Brian Cox often reminds us that Earth's own habitability is not a cosmic inevitability, is a remarkable stroke of balance. Our planet exists at the right distance from a stable star. Its atmosphere is rich in oxygen and carbon dioxide, but not too much of either. It rotates at a rate that distributes warmth and light. It is shielded from radiation by a magnetic field, and it has plate tectonics, which recycle nutrients and regulate climate over millions of years. In every one of these details lies the silent engineering of the cosmoscene, planned, unconscious, but necessary for life to thrive. So when we look to other stars, what are we really seeking? We are searching for echoes of Earth, for planets with atmospheres that breathe, oceans that churn, and surfaces that bask in starlight. And we are learning that such planets may not be rare. The Kepler Space Telescope revealed thousands of exoplanets, many of them Earth-sized and orbiting in their stars' habitable zones. Some lie hundreds of light-years away. Others, like Proxima Centauri b, are just next door on cosmic scales. We are finding these planets faster than ever, and with each discovery, our expectations grow. Yet, Brian Cox cautions us, habitability is not life. A planet can have all the right conditions and still be barren. But without those conditions, life has no chance at all. The Goldilocks Principle is not a guarantee, but a filter. It narrows the vast field of possibilities to a set of intriguing candidates, and there is beauty in this narrowing. It suggests that life, while precious and improbable, may also be a natural outcome given the right ingredients, the right timing, and the right environment. It also reminds us of how special Earth is, how unlikely, how fragile, and how essential. It is to preserve the conditions that make our own world just right. As we continue our search through space, guided by balance and possibility, we carry with us a quiet hope that somewhere in a sunlit orbit, not too far, not too close, another planet is holding its breath, waiting for us to find it. Chapter 3: Starlight and Habitability. Every planet is shaped by the star it orbits. From the first moment of its formation, a planet's temperature, weather, chemistry, and very chance at life are governed by the starlight it receives. In the search for habitable worlds beyond Earth, understanding stars is just as essential as understanding planets. For it is starlight gentle or fierce, stable or violent, that determines whether life might flourish or never begin at all. Brian Cox often invites us to think of stars not as distant pinpoints of light, but as life-shaping engines. They are nuclear forges, burning hydrogen into helium, releasing energy that radiates through space in the form of light and heat. And though we see only their surface, stars are deep, complex systems with lifespans, moods, and temperaments. Our own sun is a remarkably stable G-type, star yellow, middle-aged, and relatively calm. For billions of years, it has provided Earth with just enough warmth to keep water liquid, yet not so much as to burn it away. Its brightness changes very little over time. Its magnetic storms, though dramatic, are mild compared to many other stars. In cosmic terms, the Sun is an ideal host, but not all stars are so generous. Some, like massive blue stars, burn bright and fast, releasing immense energy, but living for only a few million years. That is far too short a time for life to evolve. From simple chemistry into complexity, let alone intelligence. Others, like small red dwarf SEM-type stars, burn slowly and can live for tens or even hundreds of billions of years. These stars are the most common in the galaxy, and they host many Earth-sized planets in tight orbits. At first glance, this seems promising. Long-lived stars could offer life an abundance of time to evolve. But there's a challenge. Red dwarfs are known for violent stellar flares, especially in their youth. These outbursts of radiation can strip away planetary atmospheres or sterilize surfaces with bursts of ultraviolet and X-rays. For a planet orbiting close enough to be warm, this proximity can be dangerous. Brian Cox approaches this dilemma with cautious optimism. He acknowledges the risks, but also the possibilities. What if some planets orbiting red dwarfs develop thick atmospheres or magnetic shields? What if life there adapts to the light in ways we can't yet imagine living beneath? The surface or under oceans, protected from flares. After all, life on Earth has thrived in the shadows, in deep caves and hydrothermal vents. Far from the sun's reach, stars also shape habitability through their lifespan and evolution. As a star ages, its brightness changes. The habitable zone moves outward. Planets once frozen may thaw. Others, once perfect, may dry up. This stellar aging means that habitability is not fixed, it drifts across time. A world might be habitable for 1 billion years, or only a fleeting moment. This temporal aspect adds a new layer to our search. It's not enough to find a planet. In the habitable zone, now we must also ask, has it been there long enough for life to emerge? Will it remain there long enough for it to evolve? The James Webb Space Telescope and its successors are now poised to answer some of these questions. By analyzing the light that passes through distant exoplanet atmospheres, we can begin to detect signs of chemistry, oxygen, methane, water vapor that may point to life. But these signs all depend, again, on starlight. It is the star that backlights the planet. It is the star that gives us a way to see dot in this way. Stars become both the gatekeepers and the guides. They are the keepers of time, the givers of energy, the clocks by which planetary histories unfold. And perhaps they are the beacons by which civilizations one day find each other flashing through the dark, across the impossible distances, carrying the quiet message, here is warmth, here is light, perhaps, here is life. Brian Cox often describes the cosmos not only in terms of physics, but in terms of elegance, and in the dance between stars and planets, between fire and rock. There is a certain symmetria, rhythm, shaped by distance, mass, and time. It reminds us that life, though fragile, does not exist in isolation. It is written into the language of light. It is bound to the pulse of stars. And so, as we turn our eyes to the heavens in search of living worlds, we are not merely seeking planets. We are listening to starlight, looking for harmony. Because somewhere in the quiet glow of a distant sun, the right conditions may have aligned once Morand. Something may be watching its sky, wondering if it too is alone. Chapter 4: Exoplanet Revolution. There was a time, not so long ago, when we knew of only one planetary system in the universe, our own. The Sun, the Earth, and its orbiting siblings were the full extent of what we could observe. The sky, beautiful and infinite, was silent on whether other Earths even existed, but that silence has been broken in the last 3 decades. A revolution has transformed our understanding of the cosmos. We now know that planets are not rare anomalies. They are everywhere. Almost every star in the night sky is likely accompanied by worlds of its own. This is the Exoplanet Revolution, and it has opened a new chapter in the human search for life. Brian Cox often speaks of this transformation with reverence. The realization that our solar system is but one among billions reconfigures how we view the universe and our place within it. In a sense, it is the moment we stopped being alone by default. The first confirmed detection of an exoplanet orbiting a sun-like star came in 1995, with the discovery of 51 Pegasi b, a gas giant so close to its star that it completed an orbit every 4 days. At the time, it seemed strange, unlike anything in our solar system. But soon, more followed. Super-Earths, mini-Neptunes, lava worlds. The catalog of planets grew rapidly, and with it, Our sense of wonder, the real explosion, came with the launch of NASA's Kepler Space Telescope in 2009, designed to stare at a single patch of sky and watch for tiny dips in starlight as planets passed in front of their stars. Kepler discovered over 2,600 confirmed exoplanets and thousands more candidates. These discoveries revealed a staggering truth. Small, rocky planets are common. Earth-sized worlds in the habitable zone may number in the billions. Imagine that. 1 billion possible Earths in our galaxy alone, each one a world with its own landscapes, skies, temperatures, and possibilities. And many orbit stars that are quieter and more long-lived than our Sun. Some are close enough that future telescopes could study their atmospheres in detail. Others, like the 7 planets of the TRAPPIST-1 system, orbit within a cosmic whisper just 39 light-years away. Brian Cox often returns to a central point, that life, complex and fragile, arises from natural processes. If the conditions are right, if there is liquid water, organic chemistry, a stable environment, then perhaps life is not a fluke, but a frequent outcome of planetary evolution. The Exoplanet Revolution feeds this idea with data. It tells us that the conditions Earth enjoys are not unique, that planets in habitable zones are not exceptional, that the building blocks for life may be as common as starlight itself. Yet, we must remember, habitability is not certainty. A planet in the right orbit may lack an atmosphere, or have one so thick and toxic that life cannot emerge. Some planets may be tidally locked, with one side scorched and the other frozen. Others may have never known liquid water. The diversity of planets is astonishing, but also humbling. Still, the tools we now possess are more powerful than ever. The James Webb Space Telescope can peer into the atmospheres of distant worlds, analyzing their chemical fingerprints. New missions like Plato and the extremely large telescope will continue the search with higher precision. We stand at the threshold of an era in which we will not only discover planets, but begin to characterize them, to know their temperatures, their clouds, their winds, their seasons, to sense, perhaps, the breath of a living biosphere from across light years. Brian Cox reminds us that this is no longer science fiction. It is science becoming. It is curiosity crystallized into instruments, questions sculpted into orbits and lenses, and it is humanity reaching quietly into the dark, searching for a reflection of itself. We may not find life right away. We may search for decades, centuries. But the Exoplanet Revolution has changed the nature of the question. We are no longer asking if other worlds exist. We are asking what they are like, and whether they too might know the spark of consciousness somewhere out there. Moment to be seen. Its signal may already be traveling through space, faint but clear. The revolution is not in the discovery alone. It is in what it means. We are no longer the center. We are no longer unique. We are one world among many, and that realization may be the first true step in understanding our place in a living universe. Chapter 5: Worlds of Water and Ice. If Earth is a blue jewel in the dark, it is not alone in its color. Scattered across the solar system are other spheres that shimmer with the promise of oceans, ice, and something more. Though they orbit far from the warmth of the sun, these worlds of water and ice may hold clues to one of the greatest questions we can ask. Could life exist beyond Earth, even here in our own cosmic backyard? Brian Cox has often described these icy moons and distant planets with both scientific precision and poetic awe. For while they are cold, silent, and seemingly lifeless, they are not empty. Beneath their frozen shells, something stirs. And in those hidden depths, we may find the first signs that life is not unique to our small blue world. Take Europa, one of Jupiter's many moons. At first glance, it appears uninviting, a pale, cracked surface of ice, laced with brown streaks and chaotic ridges. But beneath that shell lies a liquid ocean, kept warm not by sunlight, but by tidal forces. As Europa orbits Jupiter, the immense gravity stretches and squeezes the moon, creating friction and heat. This process, known as tidal heating, melts the inner layers and sustains a global ocean that may be twice the volume of Earth's. And where there is water, there is the possibility of life. Beneath Europa's surface could be hydrothermal vents, just like those found on Earth's ocean floors. On our planet, these vents teem with organisms that survive without sunlight, relying instead on chemical energy. If similar conditions exist on Europa, then life may have found a foothold there. 2 further out lies Enceladus, a small moon of Saturn. It too harbors an ocean beneath its icy crust. But Enceladus does something remarkably, sprays its ocean into space. Geysers erupt from cracks near its south pole, launching water vapor, ice, and organic molecules into space. These plumes have been sampled by spacecraft, revealing signs of complex chemistry. Brian Cox has pointed to Enceladus as one of the most promising places to search for extraterrestrial life in the solar system. Unlike Mars or Venus, where we must dig or speculate, Enceladus offers its secrets freely, flinging them into the void. All we must do is reach out and catch them. Then there's Titan, Saturn's largest moon world, unlike any other. Titan has a thick atmosphere, rivers and lakes, weather systems, and even rain. But here, water is not the liquid of life. No, it is frozen solid. Instead, Titan's lakes are filled with liquid methane and ethane. Its chemistry is alien. And yet, some scientists believe that life could still arise in such exotic conditions. Not life as we know it, but life as it could be. Beyond our solar system, discoveries continue to hint at water-rich planets and moons. Some exoplanets, known as ocean worlds, may be covered entirely by deep global seas. With the right temperature and chemistry, such planets could be ideal environments for life to evolve. But water alone is not enough. For life to thrive, it needs energy away to convert raw ingredients into something more. On Earth, this energy comes from sunlight or from chemical reactions in the deep sea. On icy moons, tidal heating, radioactive decay, or hydrothermal systems could play the same role. Brian Cox often emphasizes the subtle elegance of this possibility that life may not need the warmth of a star, that beneath layers of ice in total darkness, biology may be waiting, quiet, simple, persistent. It is a vision of life not as a rare anomaly, but as a consequence of the right conditions. Water, chemistry, energy, time, and perhaps most powerfully, is a vision that brings the search for life close to home. We need not travel to distant galaxies or unimaginable distances. The next discovery could be orbiting just beyond Saturn, waiting under ice, breathing through vents, growing, perhaps, slowly and silently in the alien oceans of a frozen world. The exploration of these moons has already begun. Missions like NASA's upcoming Europa Clipper and ESA's JUICE will study Europa and Ganymede in detail. Future missions may carry landers or submersibles designed to pierce the ice and dive into the unknown. If life is found in one of these worlds, primitive, microbial, or otherwise, would change everything. It would mean that life is not confined to Earth, that it can arise in darkness, under pressure, in cold, that biology is not an earthly miracle, but a cosmic tendency. Brian Cox reminds us that such a discovery would not diminish life on Earth, but enrich it. It would place us within a broader context. It would mean that nature wants to become alive, that life, in all its forms, is written into the fabric of the cosmos, and in that revelation, we might see ourselves more clearly not as exceptions, but as participants in a living universe. Chapter 6: Extreophiles on Earth. To understand the potential for life beyond Earth, we must first ask, what are the limits of life here? For much of human history, it was assumed that life required comfort temperate climates, sunlight, clean water, and stability. But over the past few decades, that view has been shattered. In the unlikeliest corners of our own planet, life not only survives, these organisms are called Extreophiles, life forms that flourish in conditions once thought uninhabitable. They are the ambassadors of possibility, and in many ways, they are the blueprint for the kinds of life we might discover elsewhere in the cosmos. Brian Cox often reflects on Extreophiles not just as biological curiosities, but as proof that nature is more inventive, more adaptable, and more stubborn than we ever imagined. Some Extreophiles live in boiling acid pools, where temperatures exceed 80 degrees Celsius and the pH can melt metal. Others endure the crushing pressures of the deep ocean, thousands of meters below the surface, where no sunlight has ever reached. There are microbes that survive in frozen permafrost, dormant for thousands of years, only to awaken when conditions improve. Then there are the radiation lovers organisms like Deinococcus radiodurans, which can withstand doses of radiation thousands of times higher than what would kill a human. There are bacteria that breathe iron, digest sulfur, or thrive in environments saturated with methane or arsenic. These life forms are not evolutionary accidents. They are refined, precise responses to extreme environmental pressures. And each one expands the definition of what life can be. On the ocean floor, near volcanic vents called black smokers, entire ecosystems exist in total darkness. The water here is superheated and rich in toxic minerals. Yet tube worms, clams, and unique bacteria flourish. Their energy doesn't come from the sun, it comes from chemosynthesis, a process that converts chemicals into fuel for life. This alone rewrites the rules. If life doesn't need sunlight, if it can survive in the deep, the dark, the acidic, the frozen, then why not beneath the icy crust of Europa, or in the underground aquifers of Mars? Brian Cox points to these parallels with cautious optimism. Extreophiles tell us that life may not require Earth-like conditions. It may need only a niche, a corner of stability in a chaotic world, a single crack in the armor of the hostile, and where Earth provides examples. The universe may offer reflections. Imagine a planet orbiting a red dwarf, bombarded by flares. Perhaps, beneath the surface, shielded from radiation, a microbial world has evolved. Imagine a moon with a frozen surface and a liquid ocean below. Hydrothermal vents may feed entire chains of alien organisms. Not intelligent, perhaps not conscious, but alive. There is a quiet poetry in this, that life, like a flame, can catch, even in the coldest winds, if only given a spark and shelter. Extreophiles also challenge our anthropocentric assumptions. We think of Earth as perfectly tuned for life, but perhaps it is life that is perfectly tuned for Earth, for much more. Perhaps the universe is not sprinkled with life merely where conditions are mild, but in places we have not yet dared to look, and that gives meaning to exploration. To study Extreophiles is not just to learn about Earth, is to prepare for what we might encounter elsewhere. It is to train our instruments to recognize unfamiliar signs of life. It is to recognize that life might not look like green plants or walking beings, but like thin films of biofilm, or clouds of microbial haze, or heat-loving colonies in volcanic fissures. Brian Cox often returns to one key idea: that the boundary between the possible and the impossible is not fixed, it is pushed outward by discovery. Extreophiles have already redrawn that boundary. They have turned Earth into a proving ground for cosmic biology. They whisper to us that life is not a delicate accident, but a resilient force. And so, in the quiet places of our planet and salt, deserts, acidic caves, radioactive mines, and frozen tundras, we may be witnessing nature rehearsing for life on other worlds, not with grandeur, but with persistence, not with complexity, but with endurance, and perhaps in those distant and silent corners of the galaxy, life is performing the same dance, slow, patient, hidden, waiting for the day we recognize its rhythm. Chapter 7: The Chemistry of Breath. Breathing is the most intimate connection we have with the universe. With every inhale, we draw in molecules that were once part of stars, oceans, forests, perhaps even other lives. It is a process so simple, so constant, that we rarely think of it. Yet, behind that rhythm lies a profound truth. Life is chemistry in motion, and breath is its quiet language. In the search for life beyond Earth, scientists often look for biosignatures, chemical clues in the atmospheres of distant planets that suggest biology might be at work. But to recognize life out there, we must first understand the chemistry that sustains life here. Brian Cox often reminds us that Earth's atmosphere is not a given. It is not simply the product of geology or physics. It is, in large part, shaped by life itself. The balance of gases, oxygen, nitrogen, carbon dioxide, methane, is the result of billions of years of biological activity. In other words, we live in the breath of our ancestors. Let's begin with oxygen. For the first 2 billion years of Earth's history, there was little to none. Life existed, but only in simple anaerobic forms. Then, photosynthetic organisms, tiny cyanobacteria, began releasing oxygen as a byproduct of turning sunlight into energy. At first, the oxygen was absorbed by rocks and oceans, but eventually it accumulated in the atmosphere, triggering what scientists call the Great Oxidation Event. It was a transformation. Oxygen opened the door to complex life. It allowed for efficient energy use, larger organisms, faster metabolisms, and it left a marker, chemical fingerprint on the planet that could, in theory, be detected from light years away. Now, scientists scan exoplanet atmospheres for similar signs. Oxygen alone isn't enough. Fit can be produced without life. But when found in the right balance with gases like methane, it becomes intriguing. That balance suggests something is replenishing both gases, constantly pushing against equilibrium. That something, we suspect, may be life. This is why the chemistry of breath becomes central to our cosmic search. Breath is not just oxygen. It is exchange. It is the movement of gases through an organism and back into the world. On Earth, plants take in carbon dioxide and release oxygen. Animals do the reverse. Microbes fix nitrogen, others release sulfur. The atmosphere is a dance of chemical interactions, intricate, dynamic, alive. Imagine a planet orbiting a distant star. Its light reaches us as a faint spectrum lines and colors whispering of its composition. Astronomers study those lines, looking for the telltale dips and peaks that suggest oxygen, water vapor, carbon dioxide. If the pattern is right, if the chemistry dances as it does here, it could point to something breathing, not necessarily like us, not lungs and air, but a process, a system, a metabolism. Brian Cox often speaks of emergent properties, complex behaviors arising from simple rules. Breath is such a property. It emerges from molecules seeking balance. It becomes life when those molecules organize, when they self-sustain, when they respond. Even the silence of breath tells a story. Consider Mars. Its atmosphere is thin, mostly carbon dioxide, with barely a trace of oxygen. No clear biosignature, no breath, and yet we search. We measure methane levels, watch for seasonal changes, wonder if underground pockets of microbial life could be releasing faint gas trails into the air. So far, nothing conclusive. But the fact that we can look and know what to look for is itself a triumph. It shows how far we've come. We have learned to read atmospheres as if they were stories, to see chemistry not just as numbers, but as signs of something moving, eating, growing. And as we build better telescopes and more sensitive instruments, we inch closer to reading those stories from farther away. Perhaps one day we will detect a world where oxygen and methane dance in strange harmony. Out of equilibrium constantly renewed. A world that breathes. Brian Cox would remind us to approach that moment with humility, because breath, while simple, is sacred. It is the whisper of biology in a vast, mostly silent universe. It is a sign that matter has organized itself, not just into rocks and clouds, but into something that feels. The chemistry of breath is not merely a clue. It is a connection, a bridge between our world and the possible worlds beyond. Between this quiet inhale and the millions of years it took to make it possible. Between what is and what might be. And so, as we search the stars for signs of life, we are really listening for the soft chemical rhythm of a planet that dares to breathe. Chapter 8. The Fermi Paradox Revisited. The universe is vast, almost unimaginably so, with billions of stars in our galaxy alone, many hosting planets in their habitable zones. It seems almost inevitable that life, and even intelligent civilizations, should exist elsewhere, and yet, as physicist Enrico Fermi famously asked, "Where is everybody?" This question, now known as the Fermi Paradox, is a profound mystery that sits at the heart of our cosmic quest. If life is common, why have we found no clear evidence of it? Why is the universe so silent? Brian Cox approaches the paradox with both wonder and humility. He reminds us that the silence is not necessarily absence. It might be the result of many factors, many filters, many possibilities that shape the fate of life. One explanation is that intelligent life is incredibly rare. The conditions for life may be common, but the jump to complex technological civilizations may be so unlikely that we stand alone, at least in this galaxy. At least for now. Another possibility is that civilizations tend to self-destruct through war, environmental collapse, or other means before they can communicate beyond their planet. Perhaps the challenges of technology and survival are too great. Alternatively, advanced civilizations might exist but choose to remain hidden. They could be observing quietly, respecting a cosmic non-interference principle, or communicating in ways beyond our current understanding. Brian Cox emphasizes the importance of patience. The universe is 13.8 billion years old, and our species is but a recent arrival. It is possible that signals from other civilizations have not reached us yet, or that our technology is still too primitive to detect them. He also highlights the vastness of space as both a barrier and a filter, even if intelligent life is out. There, the distances are immense. Signals weaken and degrade. The speed of light sets a cosmic speed limit. Traveling or communicating across these distances is daunting. The Fermi Paradox invites us to consider our own future, our own survival, our own impact on the planet, and our own place in the cosmic timeline. Are we the first or the last? Are we alone or simply early? These questions inspire both scientific inquiry and philosophical reflection. Brian Cox reminds us that the search for extraterrestrial intelligence, SETI, is ongoing. New technologies, new telescopes, and new strategies increase our chances of success. But more importantly, the paradox teaches us to cherish life here and now, to nurture our fragile planet, and to look outward with curiosity and hope in the silence of the cosmos. The Fermi paradox is not a discouragement, it is an invitation to explore, to learn, to wonder, and perhaps someday to hear an answer. Chapter 9: Signals in the Cosmic Noise. The universe is filled with soundless whispers, waves of energy traveling across vast distances, carrying the stories of stars, galaxies, and perhaps. Noise is like hearing a single voice in a roaring crowd. For decades, scientists have listened, pointing antennas to the sky, scanning frequencies, searching for a pattern that might mean we are here. Brian Cox often compares this search to listening to a symphony from across a vast canyon. The music is out there, but faint. It requires patience, precision, and faith that the silence is not empty. The search for extraterrestrial intelligence, or SETI, began in earnest in the 1960s, sparked by the idea that radio waves might be the universal language. Radio waves travel vast distances, can carry complex messages, and can be generated by technological civilizations. Over the years, SETI projects have scanned the skies, listening to stars near and far. They have focused on the waterhole, a quiet band of frequencies between hydrogen and hydroxyl emissions, considered a logical place for civilizations to broadcast despite all efforts. No definitive signal has been found, yet the absence of evidence is not evidence of absence. Brian Cox reminds us that our search is only beginning. The sky is vast, frequencies are many, and civilizations, they exist, may not broadcast as we imagine. There are other possibilities. Signals might be encoded in ways we don't recognize. They might use technologies beyond radio, or they might be intentionally silent. Meanwhile, natural cosmic phenomena produce their own signals pulsars, quasars, fast radio bursts that fill the sky with complexity and wonder. Decoding this cosmic noise is a monumental task. Yet, the search continues, fueled by hope and the profound human desire to connect. Perhaps, somewhere, a signal waits quiet, persistent, ready to be heard. Chapter 10: Time and the Universe. Time is the silent thread weaving the fabric of the universe. It flows forward, steady and relentless, marking the progression of stars, galaxies, and the very atoms that compose us. Yet, time is not as simple as the ticking of a clock. It is a complex dimension intertwined with space itself. Shaped by gravity and energy, Brian Cox often invites us to think of time as a river carrying us onward, never backward. The laws of physics, as we understand them, favor this one-way journey. But why? Why does time have a direction? The answer lies in entropy, the measure of disorder in a system. The universe began in an incredibly ordered state, hot, dense point at the Big Bang. Since then, entropy has increased, pushing the universe toward greater disorder. This increase defines the arrow of time. The reason why causes precede effects. Why we remember the past but not the future. And why time flows forward. But the relationship between time and the universe goes deeper. Einstein's theory of relativity revealed that time is flexible. It can stretch and compress depending on speed and gravity. Near massive objects like black holes, time slows down a phenomenon known as time dilation. This leads to mind-bending possibilities. Could time travel be real, at least to the future? If astronauts travel near the speed of light, they would age more slowly, arriving years later while more time passes on Earth. But traveling to the past remains elusive and fraught with paradoxes. Brian Cox also explores how quantum mechanics challenges our understanding of time. On the smallest scales, time may be discrete, not continuous. It might even emerge from deeper, timeless realities. As the universe expands, driven by mysterious, dark energy, time marches on, carrying galaxies farther apart, stretching the cosmic fabric. In contemplating time and the universe, we confront profound questions about existence, change, and the nature of reality itself. Time is both a measure and a mystery, a river carrying us through the vast, silent cosmos. Chapter 11: Black Holes and Time. Black holes are the universe's ultimate paradox, regions where gravity crushes space and time into extremes we can barely comprehend. Brian Cox often describes them as cosmic laboratories, places where our understanding of physics is pushed to its limits. At the edge of a black hole lies the event horizon, a point of no return. Anything crossing it is lost to the outside universe, swallowed by the singularity where density becomes infinite. But black holes are not just cosmic vacuum cleaners. They distort time profoundly. Near a black hole, time slows dramatically compared to distant observers. This phenomenon, predicted by Einstein's general relativity, means that an astronaut falling toward a black hole would experience time differently from someone watching afar, in theory. This time dilation could allow an observer near a black hole to see the future of the universe unfold rapidly outside their vicinity. Yet, what happens inside the event horizon remains a mystery. The laws of physics break down, and quantum gravity, the unifying theory yet to be discovered, must take over. Brian Cox points out that black holes challenge our concepts of time's flow, causality, and the fabric of reality. They force us to confront questions about information loss, quantum mechanics, and the nature of existence itself in the shadows of these cosmic giants. Time bends, stretches, and warps, revealing the universe's profound complexity and the limits of human understanding. Chapter 12: Wormholes and Time Travel in the Vast Cosmic Landscape. Wormholes stand as theoretical bridges, shortcuts through the fabric of space-time, connecting distant points in the universe. Brian Cox often describes them as tunnels that might fold space and time, potentially allowing travel across vast distances or even through time itself. The concept originates from Einstein's general relativity, which permits solutions to the equations describing spacetime that include these hypothetical passages, also called Einstein-Rosen bridges. Wormholes could, in theory, link to separate regions of space and time. If such structures exist and could be stabilized, they might enable journeys faster than light would allow, or perhaps even to the past or future. But reality is complicated. Wormholes, if real, would require exotic matter substances with negative energy density to keep their throats open and prevent collapse. This kind of matter has never been observed and remains speculative. Moreover, the existence of wormholes raises profound paradoxes. Could one travel back in time and alter the past? If so, what happens to cause and effect? These questions lead to paradoxes such as the famous grandfather paradox, where a time traveler might prevent their own existence. To address these problems, physicists propose ideas like the many worlds interpretation, where each change creates a new parallel universe, avoiding contradictions. Brian Cox emphasizes that wormholes remain speculative. They stretch our imagination and challenge our understanding of reality. But no evidence has been found yet. Still, they serve as powerful tools in theoretical physics probes into the possibilities of space-time, quantum gravity, and the ultimate nature of the cosmos. Whether wormholes are science fiction or future science, Their study expands the horizons of human knowledge, inspiring us to explore the profound mysteries of time and space. Chapter 13: The Grandfather Paradox and Time Travel Dilemmas. The idea of traveling through time, especially to the past, opens a Pandora's box of logical puzzles. Chief among these is the Grandfather Paradox, a thought experiment that questions the very possibility of altering history. Imagine a time traveler who journeys to a time before their grandfather had children and accidentally prevents their grandfather from meeting their grandmother. If this happened, the traveler's parent, therefore, the traveler never have been born. But if the traveler never existed, how could they have gone back in time to change anything? This paradox highlights a fundamental conflict between the idea of free will and the fixed nature of history. If the past can be changed, then cause and effect unravel. If it cannot be changed, then the traveler's actions are somehow constrained. Physicists and philosophers have proposed several ways to resolve this dilemma. One is the idea of self-consistency, where events in time are fixed, and any actions a time traveler takes were always part of history. In this view, paradoxical situations simply cannot occur, because history corrects itself. Another intriguing proposal is the many worlds interpretation from quantum mechanics. This suggests that every decision creates a branching of the universe into parallel realities. Traveling to the past would create a new timeline, allowing the traveler's actions without erasing their original history. This interpretation opens fascinating possibilities, but also complicates our understanding of identity, causality, and the nature of reality. There is also the bootstrap paradox, where objects or information exist in a causal loop with no clear origin. For example, a person receives a piece of technology from their future self, then later sends it back in time. The technology exists without ever being created, an apparent paradox of cause and effect. Brian Cox approaches these dilemmas with a blend of scientific skepticism and wonder. While they highlight the challenges of time travel, they also push the boundaries of our understanding. Time travel to the past remains theoretical and fraught with difficulties. Our current physical theories allow for intriguing possibilities, but also impose limits. The universe's consistency seems to prevent contradictions, but the precise mechanisms are still unknown. Ultimately, these paradoxes invite us to explore deeper questions about time, causality, and the structure of reality itself. In pondering the grandfather paradox and its cousins, we confront the limits of our knowledge, the profound mysteries at the heart of time. Chapter 14: The Bootstrap Paradox. Time travel introduces puzzles that challenge our understanding of cause and effect. Among these, the bootstrap paradox stands out as a mind-bending enigma that twists logic into loops. Imagine a time traveler who receives a watch from their future self. They keep the watch for years, then travel back in time and give it to their younger self. The watch exists in a closed loop with no clear origin. Where was it created? Who originally made it? This paradox reveals the strange consequences of closed causal loops situations where cause and effect seem to form a circle without a beginning. The term bootstrap comes from the idea of pulling oneself up by one's bootstraps, an impossible feat in physics and philosophy. The bootstrap paradox suggests objects, information, or even people might exist without an origin, sustained by the loop of time travel. The paradox raises profound questions. Can information or matter exist without ever being created? Does this violate the principle of causality? How does it fit within known physics? Brian Cox often points out that while these paradoxes are fascinating thought experiments, they also highlight the limitations of our current understanding. Classical physics does not allow such loops, but some solutions in general relativity permit the theoretical existence of closed time-like curves, paths in space-time that return to their own past. Quantum mechanics adds another layer of complexity. Some interpretations suggest the universe might allow these loops, but only under conditions that prevent contradictions or violations of causality. The bootstrap paradox challenges our notions of time as linear and cause as preceding effect. It forces us to consider time as a dimension where causality might be more flexible or even cyclical. While no experimental evidence supports the existence of such loops, the paradox remains a vital part of discussions on time travel and the nature of reality. It serves as a reminder that our universe might hold deeper truth concepts that defy our everyday experience and stretch the imagination beyond familiar bounds. Chapter 15: The Many Worlds. Interpretation. The mysteries of time travel and quantum mechanics intersect intriguingly in the many worlds. Interpretation of quantum physics, proposed by Hugh Everett in the 1950s. This idea suggests that every possible outcome of a quantum event actually occurs in its own separate, parallel universe. Imagine a decision point where the universe splits, creating multiple realities that coexist side by side. In one universe, you take one path, in another, a different choice. This branching happens constantly. At every quantum event, Brian Cox often highlights how this interpretation offers a potential solution to time travel paradoxes. If traveling to the past creates a new timeline, new different branch, then altering past. Events doesn't erase the original history. Instead, it creates a parallel reality where different outcomes unfold. This idea elegantly sidesteps paradoxes, like the grandfather paradox, because actions in the past affect only the new timeline, leaving the original untouched. The many worlds interpretation challenges our intuition about reality. It suggests that the universe is not a single thread, but a vast, branching tree of possibilities, while difficult to test experimentally. The interpretation has gained traction because it resolves certain quantum mysteries without invoking wave function, collapse, or randomness. It also invites philosophical questions. What does identity mean if there are countless versions of ourselves? How do we understand free will in a multiverse? Brian Cox often encourages reflection on the beauty and strangeness of this view. Cosmos, richer and more complex than we ever imagined. Whether or not the many worlds interpretation is correct, it opens our minds to the profound possibilities lurking at the edges of physics and the mysteries of time, choice, and existence. Chapter 16: Time Crystals and the Nature of Time. In recent years, the discovery of time crystals has fascinated physicists and challenged our understanding of time itself. Unlike ordinary crystals, which have repeating patterns in space, time, crystals exhibit patterns that repeat in time, oscillating without energy input, defying the traditional rules of thermodynamics. Brian Cox describes time crystals as a new state of matter, one that breaks time translation symmetry. In simpler terms, while most physical systems settle into equilibrium, time crystals remain in perpetual motion, cycling endlessly between states. This discovery opens exciting questions about the fundamental nature of time. Could time itself have a deeper structure beyond our everyday experience of flowing forward? Some scientists speculate that time crystals could be harnessed to explore quantum time phenomena, possibly offering new ways to understand how time emerges from underlying physics. Furthermore, time crystals might offer clues toward the elusive goal of uniting quantum mechanics and general relativity, the two pillars of modern physics that currently stand apart, though time crystals do not enable time travel in the science fiction sense. Their unique properties expand the boundaries of what is physically possible, encouraging us to rethink time not just as a passive dimension, but as an active player in the universe. Brian Cox often reminds us that such discoveries are milestones on our journey to comprehend reality's deepest layers. Time crystals invite us to look beyond classical views and imagine a cosmos where time itself dances to rhythms we have yet to fully understand. Chapter 17: Quantum Entanglement and Time Travel. Quantum entanglement is one of the most fascinating phenomena in modern physics. Mysterious connection between particles that seems to transcend space and time. When two particles become entangled, the state of one instantly influences the other, no matter how far apart they are. Brian Cox often describes entanglement as a kind of cosmic dance, where particles share information in ways that defy classical intuition. This phenomenon raises tantalizing questions about the nature of time and the possibility of time travel. Could entanglement allow information, or even matter, to travel backward or forward in time? While current physics does not permit faster-than-light communication or traditional time travel via entanglement, some theoretical models suggest that quantum connections might offer glimpses into temporal phenomena. Researchers explore whether entanglement can be harnessed to create quantum teleportation, transmitting information instantaneously across distances. This has practical applications in quantum computing and secure communication. Moreover, some speculative theories propose that entanglement could play a role in bridging quantum mechanics and gravity, potentially illuminating the nature of space-time itself. Brian Cox cautions that these ideas remain at the frontier of physics, fascinating but far from established science. Still, entanglement invites us to rethink the fabric of reality, where space and time may be intertwined in ways that challenge our deepest assumptions. The mystery of entanglement continues to inspire scientists and philosophers alike, as they seek to unravel the profound connections hidden within the quantum world. Chapter 18: The Search for Time Machines. The idea of building a machine capable of traveling through time has long captured human imagination. From ancient myths to modern science fiction, time machines represent the ultimate dream of transcending the constraints of our linear existence. Brian Cox approaches this concept with a grounded yet hopeful perspective. While true time machines remain speculative, physics offers theoretical frameworks that suggest they might be possible, if not with current technology. Then, perhaps, in the future, theoretical constructs like wormholes, cosmic strings, and closed time-like curves have emerged from Einstein's general relativity and quantum mechanics. These exotic solutions imply that space-time could be manipulated to create shortcuts or loops through time. Scientists are actively exploring these ideas, seeking to understand the physical laws that would allow or forbid time travel. Efforts are subtle and indirect, from studying particle accelerators to investigating quantum phenomena that hint at temporal anomalies. Yet, immense challenges remain. Maintaining stable wormholes would require exotic matter with negative energy, something not yet observed. Paradoxes inherent in time travel, like the grandfather paradox, demand resolutions that current physics has yet to fully grasp. Despite these obstacles, the search for time machines drives innovation and deepens our understanding of the universe's fabric. Brian Cox often emphasizes that even if time machines never materialize, the pursuit itself illuminates profound truths about space-time, causality, and the limits of reality. In this quest, humanity stands at the frontier of knowledge, where imagination meets rigorous science, a place where dreams and reality intertwine. Chapter 19: The Limitations of Current Theories. Our journey into time travel and the nature of time reveals a landscape both rich and mysterious. Yet, as Brian Cox often reminds us, our understanding remains incomplete, framed by theories that work well within certain domains but falter at extremes. Einstein's theories of relativity revolutionized physics, showing how time and space intertwine and bend under gravity. Quantum mechanics opened the door to the strange and probabilistic behavior of particles. But these two pillars remain incompatible at a fundamental level. The quest for a unified theory of everything that merges gravity with quantum mechanics continues to challenge physicists. Current theories struggle to explain phenomena such as the nature of singularities inside black holes, or the true origin of time itself. Concepts like wormholes or closed time-like curves are mathematically plausible but physically unverified. Moreover, the paradoxes of time travel hint at inconsistencies that our current frameworks cannot resolve. The nature of causality, the flow of time, and the fabric of reality may require new physics beyond what we know. Brian Cox emphasizes humility in the face of these unknowns. Scientific progress is iterative, building on the known while probing the unknown. The limitations of our current theories are not failures, but signposts, markers pointing toward deeper truths waiting to be uncovered as we push the boundaries of knowledge. We remain explorers at the edge of a vast cosmic ocean, navigating by stars that sometimes flicker, sometimes shine brightly. Our theories evolve, as must we, embracing mystery and wonder in equal measure. Chapter 20: The Ethical Implications of Time Travel. The possibility of time travel invites not only scientific inquiry, but also profound ethical questions. Brian Cox reminds us that with great power comes great responsibility, and the ability to manipulate time would be no exception. Imagine possessing the ability to travel to the past or future, to change events, to alter outcomes. Such power could heal injustices, prevent disasters, or rewrite history. Yet, it also poses dangers that challenge our moral frameworks. Would altering the past erase lives or memories? Could it destabilize the very fabric of reality? The ripple effects of small changes might be vast and unpredictable. Moreover, who would decide how and when to use time travel? Would it be accessible to all or controlled by a few? Could it deepen inequalities or create new conflicts? Philosophers and ethicists speculate on these dilemmas. The concept of temporal justice emerges the idea that actions across time should be governed by fairness and respect for autonomy, both past and future. Brian Cox also highlights the potential psychological impact on travelers themselves. Experiencing multiple timelines or witnessing future tragedies might weigh heavily on human minds. The ethical implications extend beyond individuals to society and the environment. Time travel might tempt us to undo mistakes, but it could also foster complacency or arrogance. Assuming consequences can always be reversed, in fiction and theory alike. These questions urge caution and reflection as our understanding of time deepens. So too must our commitment to wisdom and humility. Time travel is not just a scientific frontier. It is a moral one in contemplating the power to shape time. We confront the essence of what it means to be human, responsible, fallible, and hopeful. Brian Cox encourages us to carry these lessons forward, whatever the future holds, reminding us that the true journey is not just through time, but through understanding. Conclusion: a universe woven with time. Time, it cradles every breath, every thought, every star that has ever burned, and every mind that has dared to wonder. Over these chapters, we've walked along its edge, tracing its mysteries, its paradoxes, and its place at the heart of the universe. And still, it remains elusive. Brian Cox often speaks of the cosmos not as a thing, but as a story, a living, unfolding narrative told through light, energy, gravity, and above all, through time. In this narrative, we are brief characters, flickering and fragile, yet gifted with the power to reflect, to ask, to seek. We have explored the scientific definitions of time and our subjective perception of it. We have felt its arrow guided by entropy and watched it warp near the gravity wells of black holes. We've imagined shortcuts through the folds of space-time wormholes and time machines and considered the strange consequences they imply. We've confronted the grandfather paradox, the bootstrap paradox, and dared to question whether causality is a lore merely a habit of thought from the quantum entanglement of particles. across vast gulfs of space to the ghostly symmetry of time crystals. We've seen how time might not be as fixed or as linear as we once believed. And perhaps most moving of all, we've allowed ourselves to ask, what if? What if time travel were possible? What would we do with such a power? Would we change the course of history, rescue lost futures, or simply seek understanding? These are not just questions for science. They are questions for philosophy, for ethics, for the human spirit. In the silence between seconds, there lies a truth that Brian Cox returns to again and again. That the universe is not just stranger, is stranger than we can imagine. And yet, through reason, imagination, and wonder, we begin to grasp it piece by fragile piece. Time travel may still live in the realm of speculation, but its pursuit brings us closer to the heart of reality. Every paradox invites a deeper theory. Every contradiction suggests a missing truth. And every impossible idea is a mirror, reflecting the limits and the potential of the human mind. Perhaps one day we will find a way to step beyond the present, to explore other moments as freely as we now explore space. Or perhaps time's flow is forever forward, its past unreachable, its future forever just out of reach. Either way, the journey continues not only through time, but through understanding, and that journey is, in itself, a form of time travel, carrying us from ignorance to insight, from curiosity to knowledge, from wonder to meaning. So we return to where we began, not with a machine or a map or a key to the universe, but with a question as old as consciousness and as vast as the stars. What is time? We may never answer it fully, but in seeking, we become part of the story it tells.